pleasure for me to be here in Barcelona, a city I like very much. And I'm going to tell you about a story about one of the key problems of uniting quantum mechanics and gravity, which is the whole issue of divergences in what should be small corrections. So let's just begin with a little bit of the early history of the subject. So Dirac, in 1927, really solved the problem of electromagnetism in his paper, Quantum Theory of Emission and Absorption of Radiation. And this is where the relativistic treatment of the electron was explained, this strange four-component but not vectorial quantity that he introduced for the spinors. And all of that has gone into the groundwork of quantum field theory. Now, his treatment of quantization was basically to take the electromagnetic field and split it up into creation and annihilation of states for which were described by harmonic oscillators with corresponding creation and annihilation operators to create and absorb them. And then we had a strong development through the work of Pauli, Wigner, Jordan, Heisenberg, Fermi in establishing the early theory of quantum electrodynamics. Now, this worked well at the leading order, what we call the tree level of quantum field theory. But there was a problem that soon revealed itself. And of course, they didn't actually talk, when I just mentioned tree, I'm already using a more modern language in a topological expansion of the theory, in perturbation theory. But as they went out to higher and higher orders in the coupling constant expansion, the electric charge, they started running into a key difficulty, which is there are integrals, just ordinary explicit integrals, which, however, are divergent. And they're integrals, a key way of handling the perturbation expansion is to expand in plane waves dependent upon a certain momentum, but the momenta go out to infinity, and the integrals involved divergences in the upper limit. If you make the integral finite formally by integrating only up to some upper limit, you found that as you took that limit away, the integrals became infinite. And this was noticed by Oppenheimer, and then also a paper by Bloch and Nortzig, and Vicky Weisskopf, of course, later on, Director General of CERN. So this was a problem that was burgeoning in ordinary quantum electrodynamics. They could see this as going to be a key issue. But then we come to attempts to quantize gravity. And in the same year, 1927, Leon Rosenfeld, who's Belgian, but working in Paris, was writing some of the very first papers on quantum gravity. Actually, people tend to think that the subject of quantum gravity began in his 1930 paper, but in fact, I found this nice paper by Peruzzi and Rocci on the early history. In fact, he was at the École Normale, and already in 1927, he was working on it. And it's strange, when you look back at the papers, you find it's extremely modern. He's doing Kaluza-Klein theory, of course, which is now part and parcel of the way we look at string theory. We have a five-dimensional space-time. Of course, the reason was he was trying to look at a theory, given the burgeoning success in treating electrodynamics, we wanted a theory that included electrodynamics. So, of course, five-dimensional Kaluza-Klein theory reduced to four dimensions produces gravity and an electromagnetic and a Maxwell field. So it was a natural thing to try. It was also at the École Normale, which of course nowadays we think of Gumer and Juliat and the other colleagues at the École Normale as one of the key centers of modern work in supersymmetry and quantum gravity, but already back in 1927, research in quantum gravity was going on. So he was focusing on the works of I think there's supposed to be a slash through that L, it's Polish, Kaluza, and Oskar Klein. In fact, Oskar Klein is the father of my thesis advisor's wife, Elspeth. So, Rosenfeld was beginning the work on quantum gravity, and Then, about a decade later, Werner Heisenberg started to raise a problem about the application of quantum techniques to gravity. Of course, in the meantime, not totally satisfactory, but people could sort of deal with it, handling the problems of infinities in quantum electrodynamics were making their way forward. But Werner Heisenberg pointed out that if you're going to look at gravity, you're going to have a much more serious problem. And the key problem is Newton's constant, that it's dimension full, as opposed to the fine structure constant in electromagnetism. Square root of 4 pi is an ordinary number, 1 over 137 point stuff, right? In gravity, Newton's constant carries dimensions, and that will give a proliferation of these infinities problems of worse and worse structure. At least in electrodynamics, you could see the structures, there were a finite number of them, you had to deal with them somehow, but in gravity, it's just going to explode. And here, in fact, is the 1938 paper by Heisenberg. Now, indeed, of course, 1938 had all sorts of other meanings in history, Kristallnacht and so forth, and this led to a decade-long pause in fundamental science. Little work was done during the dreadful decade following World War, in the course of World War II, on relativistic quantum field theory. Nuclear physics, of course, did get a significant advance. But after the war, and as the world was picking itself back together, the first serious conference was held in Shelter Island. I don't know if you know where Shelter Island is. Long Island has 2 forks at the end. The South Fork is the fancy one where the rich people live. The North Fork is a much more popular fork where fishermen and so forth live. And in between, there's this kind of bay, and in the middle of the bay is Shelter Island. So that was a conference in 1947. Feynman was there. The key names of quantum field theory were attending that conference, and Hans Bethe. The issue of infinities was raised, not particularly in gravity, by the way, but in electrodynamics. And Hans Bethe, on the train back, made a back-of-the-envelope calculation of a way of treating the infinities, which turned out to be really seminal. The key context here was that the experimental results of Lamb and Rutherford were out, and these were just discussed at the Shelter Island Conference. And so they had a particular value for the shift in the energy levels, the spectral lines of the hydrogen atom. And the question was how to explain this. And Bethe understood this had to do something with these pesky quantum corrections that seemed to be infinite. And so he invented a procedure, kind of off-the-cuff procedure to handle them. And now, what were they doing before this about the infinities? I've been told, I don't have a real textual confirmation of this, but an attitude at the time was these infinities really are zero. Let's just forget about them. But the thing about the Lamb-Rutherford result was, no, it's not zero. It's a little bit like the cosmological constant, which also people thought was zero. And now we know it's a tiny number. Whoa. So now you have to really work. Okay? Well, back then, the Lamb shift gave rise to a real need to explain this small number where it comes from. And so that was the motivation for Hans Bethe to try to do a better job. So this, as I say here, changed the psychology of the situation in a rather important way, and it led to a procedure known as renormalization for handling the infinities. And this was the work of Tomonaga, also rather early. In fact, I guess as the war was threatening, I think back in 1937, Tomonaga, rather independent of all the others, Tomonaga, Feynman, Schwinger, and Dicey. So this is now what we now, the relativistic quantum electrodynamics. Beforehand, people were quantizing basically in a Hamiltonian formulation, which is space and time separated. And so now maintaining Lorentz invariance became possible, and this required understanding properly how to handle the infinities. Our All right, in this sort of talk, I could go through and tell you more about the details of how to handle the normalization process, but I'm not going to. I can do that, discuss that in discussions if you want. Let me just give you some flavors of what you have to do. The first thing is to make it definite what you're talking about. You just can't write a sideways 8 and say that's it. You have to make the formally divergent integrals finite by a procedure we call regularization. So there are various styles of regularization. One style of regularization is to take these integrals over space and time, rotate the time by t into minus I tau, what we call Euclideanizing it. Now the integral over all momenta can be treated as a sphere in 4-dimensional space, and you can just go out to a certain radius lambda in the 4-dimensional space. That's called the straight momentum curve. It's the simplest form of regularization. Another form of regularization that is commonly used is called dimensional regularization. If you consider doing the integrals in d-dimensional spacetime, you get formulas that depend upon d, then you analytically continue d away from 4, a little bit away, 4 minus epsilon. And in particular, you find expressions that now develop a pole in 1 over epsilon goes to the infinities. So dimensional regularization is actually very important for some of the rest of the story. Now, you're going to have to give up something in the context of renormalization, which is the next step. You give up any attempt at calculating a certain number of quantum corrections. Basically, you're just going to have to go down the hall, and knock on the experimentalist door and say, "Excuse me, could you tell me what the mass of the electron is? I can't calculate it." So you give up a certain number of things, and then in order to handle the rest of the theory, you assign in the formulation of the theory, which is in terms of Lagrangian and Lagrangian field theory with action, you assign a certain number of quantities, we call them bare quantities, formally divergent values, but in the context of your chosen regularization. Right? So you make an expansion in terms of supposedly classical value plus quantum corrections and so forth. You know that you can't sum it up to something that you can calculate, but it's only the sum that's going to be meaningful. And so there's a series of values with very formally divergent quantities involving this regularization, and you choose these divergent quantities in the expansion of the coupling constants and masses precisely just such as to cancel the things you don't like coming out of the diagrams. So you get rid of the infinities. What's left over is a finite quantity, and then you ask times theta, how does it do? And it does a fantastic good job. And it worked so well in explaining the lab shift that people knew that although this is horrible and particularly Feynman hated it, he thought it was a hat trick of some sort, but there's clearly truth in it. And now quantum electrodynamics is the most accurate physical theory that we have. A number, I can't remember, it's 13 significant figures or something like that. G minus 2 values for the muon. So, although it's ugly, it's working, right? And it makes the perturbation theory well defined. Now, in a theory where you can do this by a finite number, you have to give up, you have to agree to knock on the experimentalist door a finite number of times. If you have to continue knocking indefinitely, it's going to get tired. Right? So the theory, if it has a finite number of such renormalizations, you call them renormalizable. And in the QED, this requires renormalization of the electron's mass, its charge, and another renormalization called the wave functions, the scaling renormalization of the electron field itself. Okay, and then that makes the theory finite, and you can calculate things, and it really works very well. Now in gravity, we come back to Heisenberg. The problem is the dimensional character of Newton's constant, and it gives rise to this proliferation of different types as you go up or higher and higher order, so the experiment is going to get tired. Whether it's totally useless or only halfway useless is a subject that Steven Weinberg has liked to discuss, and that indeed is an interesting philosophical topic we can get into later on. What can you do with a non-renormalizable theory? But gravity is, on the surface of it, clearly non-normalizable, and this is the problem that Heisenberg noticed back in 1938. So here we have, for example, important classic diagrams at 3 loops. We'll see that later on. Now, in the Feynman approach, perturbative corrections are organized topologically according to the number of loops. You can also organize them according to the number of powers of coupling constants, but watch it. In gravity, we take 1 over 8 pi times Newton's constant, sorry, 8 pi times Newton constant, we call kappa squared. And then the kappa is an expansion parameter dimension for, watch it. It's a length, Planck. And it comes in the expansion of Einstein's Hilbert action. You do something that relativists don't like. You write the metric as flat space metric, a to mu nu, plus a little fluctuation, h mu nu. And that's what causes apples to fall and gravity waves and so forth. Right? But then, because Einstein's theory is highly nonlinear, the expansion goes on to all orders. It's actually a to mu nu plus kappa h mu nu. And so you see the kappa comes to infinite order. So counting kappas is not very useful. I would say the power counting weight of the gravitational field is 0. But the derivatives in the gravitational action have weight 1. We'll come back to that later on. Now, we find that I can do a little power counting if we have time to know. Is there a definite fixed end to this, Sylvia? Or we saw it elastic on the time I can take? Yeah. I basically plan to know. Just do a little calculation maybe. So here's a one-loop diagram. So you write G mu nu is equal to a to mu nu plus kappa h mu nu. And then, of course, you have the Einstein action. G is the determinant of the metric G mu nu, and then we have the Riemann, the scalar curvature of the Riemann tensor. R mu nu rho sigma is equal to, well, there would be mu d nu G rho sigma. I'm not going to write the precise thing down. Anyway, note there are 2 derivatives in it. Okay, and so here, when we expand this, it's highly nonlinear. When you expand this in G mu nu, you see that there are 2 derivatives, which basically means in momentum space there are 2 factors of momentum here, 2 factors of momentum there. This propagator comes from inverting the kinetic operator, so that's a 1 over k squared here. It's actually, you have to do momentum conservation, but let's just do it roughly. There's 1 over k squared there, and then there's an integral over all momentum. So in fact, you see that what we have here is something, if you have a straight momentum cutoff, it's going to be what we call cortically divergent. Okay, that's the rough, very rough power thing. Now, in dimensional regularization, we don't actually see this power law divergence. There are other things that can happen. You have to remember that they're really momenta on the external line. So there are terms here. If I write the full thing out, actually, what we have is something that goes like p to the 4th, and suppose we have an h mu nu here and an h rho sigma here on the external lines, and then you have something with p to the 4th, h mu nu, h rho sigma, and I have to write something that's generally covariant involving 4 derivatives and 2 fields for this diagram. It has to be generally covariant. So actually, what it's going to look like, if I go back to coordinate space, it's d4x, please, square root minus g, I need 4 derivatives. R has 2 derivatives. So basically, it's curvature squared. You see, the original action was just the Einstein-Hilbert action, and then we come up with something that's a different structure. Go to higher and higher loops, gets worse and worse. The net degree of divergence, let's call that delta, the maximum degree of divergence is d minus 2 times the number of loops plus 2. And you see, as you go up the loop order, it goes bonkers. Okay. So that's what I said here. The naive degree of divergence is d minus 2L plus 2. By the way, what's left over, when I said you don't see these power law divergences, of course what you see left over is something like d4 k over k to the fourth. If you're pulling 4 momenta outside the diagram onto the external lines, that chord you have to push and pull. There's 1 over k that comes inside. And this is a logarithm. It's a log of some scale, maximum scale. And by the way, logarithms, you don't like to have logarithms of purely dimensional quantities. So there's always a reference scale in there as well, called mu. And that will come back later in the story too. The key point is in dimensional regularization, what you see is a logarithm. And that's an important part of the structure. Okay, so this is basically telling you the nastiness of the story as you go up order by order, and you can see that it's getting out of control. And you can also do the similar counting in other space-time dimensions, and it gets worse and worse. Okay, so the only nice dimension, of course, is 2, about which I'm going to have another whole discussion. All right, now, this was an anticipation. I just scribbled some things on a blackboard, but the actual calculation was done by 't Hooft and Veltman in pure general relativity. And they found, indeed, so 4 minus 2 times 1 plus 2 is 4, as we just saw here. 't Hooft and Veltman evaluated the one-loop diagrams in pure general relativity and found that you have counterterm structures involving the curvature squared. There are actually 2 counterterm structures. Counterterms means if you're going to play this renormalization game, even in a non-renormalizable theory, you just subtract the infinities and deal with the residual finite results. The problem is that going on to higher and higher orders, you're going to keep on doing this. The experimentalists get sick of you. And you have to debate whether any meaning is left in the theory. But at the one-loop level, we're facing curvature squared counterterms. The counterterm is what you include in the theory in order to subtract the infinities from diagrams. So, the 2 counterterms that you need actually is not the one that I wrote. I'm going to come to that in a second. But they're Ricci squared and R squared. R is the trace with a metric of the Ricci tensor. Now, there's something special about these 2 counterterms, which is that, remember, in the absence of any other matter, if we're dealing with pure gravity, the Einstein field equations just say that the Ricci tensor, of course, the Ricci tensor is the trace on 2 of these indices, like mu rho, of the Riemann tensor. But R mu nu, the Ricci tensor, 2-index Ricci tensor equals 0 is the Einstein field equation. That allows you to get away with eliminating these particular divergences in a different fashion by making a variation of the field, G mu nu, by a term that involves R mu nu. Then it bounces off, if that's a little variation of the field, it'll bounce off the original Einstein action R, and it can produce exactly these 2 terms in leading order, and then there's homework for you left on for higher order, which you eventually should come to, but you can get rid of these initial infinities by a field redefinition renormalization. And moreover, there's a general theorem in quantum field theory that the S matrix is invariant under field redefinition, changes the variables. So these particular infinities may not be so important. The reason that you got away with this in pure gravity has to do with this other feature. Remember, I said I didn't. What I wrote down here actually is the one that doesn't vanish subject to the classic field equation, but we have the Gauss-Bonnet theorem, which says that the integral of root minus g curvature squared minus 4 r mu nu squared plus R squared is actually a total divergence. In fact, what it is, the quantity is in fact the Euler number of space-time. It's a topological invariant. But if you're just expanding around flat space, you see that black space is topologically trivial, this quantity vanishes. So you can trade in the integral of curvature squared for combinations of r minus squared and r squared. So that's the combinations they found with plenty numbers from the explicit calculation. And thereby, in pure gravity, you can get rid of the infinities in the one loop level by just a field redefinition, renormalization. Okay, well that raises the question, is this luck going to go on forever? Maybe it was all okay after all. These infinities are somehow vanishing or illusory. To answer that requires going to two loops, and that's a much harder calculation. It was done by Goroff and Sanyati back in 1985. Here are the relevant two-loop diagrams, two-loop Feynman diagrams. They get worse and worse and worse. And taking a hint from the discussion we just gave about imposing classical field equations to eliminate discussing things that could be eliminated by field definitions, you find there is now, well, let's see, 2 times 2 plus 2 is 6. 6 dimensions of each Riemann tensor has dimension 2. You'd be looking at Riemann cubed. Okay? So indeed, there's a Riemann cubed counter term, and this is their hard work. You have a definite coefficient in front times 1 over epsilon in dimensional regularization. So it's really there. It's not just Heisenberg's worry. It really happens. And now this you cannot get rid of by any field redefinition. So this is the confirmation of the non-renormalizability of gravity. And it goes on and on and on. Okay, so what to do about the infinities? So Heisenberg's problem is, has to be taken seriously, and there are a couple of different points of view that I can imagine. The first one I could call perhaps the Dirac attitude, which I'm going to come back to a little bit later on in the talk, which is find the right theory. And hope that with suitable symmetries or other special properties, this nice behavior of pure gravity at one loop maybe can be continued and you can get away with it. Right? So it requires careful arrangement of gravity plus matter fields in the hope that the ultraviolet infinities will magically cancel in a fashion somewhat similar to what happened for development. And this, in fact, is the underlying motivation of supergravity and continues on into string theory. That is to say, take the right theory. And I don't have a direct quotation for this, but I've heard it ascribed to Dirac. The problem is you haven't got the right theory. Another point of view could be to change your attitude towards renormalizability. Maybe let the theory try to tell you what it wants as you calculate on. Maybe you have a theory like general relativity, but you should allow the theory's own counterterms to tell you what you should be starting with. And this underlies the study of higher derivative extensions of gravity. It's a point of view that I've heard Dirac and Toft expressing rather recently. It also lies at the heart of the asymptotic safety approach, which does not involve careful sort of crystalline combinations of gravity and other fields, but it's rather how do you handle the quantization problem of gravity itself with perhaps higher order terms included from the start. Don't limit yourself to 2 derivative terms. And another point of view could be changing the quantization procedure away from the way that we learned from Feynman and Dyson and so forth, perhaps taking a better account of non-perturbative aspects of the theory. Of course, the Feynman, Dyson, etc. approach to quantization is inherently perturbative. Expanded eta plus kappa h nu, and then go on. Well, there could be something hiding in these, maybe the infinities sum up to zeros. So this is underlying the approach based upon Ashtekar variables, loop one gravity, and spin foams. I'm not going to have time to talk about that, but I mentioned it here as another line of approach. I'm really going to talk about these first two. So let's talk about the higher derivatives for a little bit. As you've seen, the Toft and Veltman's calculations gave rise to curvature squared one-loop counterterms. can be rewritten in terms of r mu squared and r squared. And as we've seen, you may decide to handle those at one loop by a field redefinition normalization, but you could choose a different attitude towards that problem and not do the field redefinition, but actually do a standard renormalization. That is to say, go back to the formulation of the theory, the original action, and include such terms. If you went to the two-loop level where you had curvature cubed, you're going to have to do this anyway. So do it already at one loop. Include r mu squared and r squared terms in the starting action. Go back and re-look at the ultraviolet problem and see what you see. So this suggestions were made by Utino and DeWitt, Stanley Deser, Stephen Weinberg, and I did the calculation. Okay, so here we start with the gravitational Lagrangian. I've written it in this form, my more favorite form, Einstein-Hilbert action. I've written it in terms of Weyl squared. So very nice picture of Weyl next door. The Weyl tensor is the Riemann tensor with its traces removed. Okay, so it's another way that you could write these curvature squared terms as Weyl squared and r squared. You can write it as r mu squared and r squared. You can write it as curvature squared and r squared in different styles using Gauss-Bonnet. So, and of course you have to mix the coefficients up a bit if you, depending on the style. I like to write it this way for the following reason. You're going to come to that in a minute. First of all, as I say, good news and bad news. The power counting now is stabilized by this inclusion of the curvature squared terms in the starting action. And it's this delta equals e minus 2 alpha plus 2. This term goes away. And in fact, it just becomes delta equals 4 to all orders. It's stable. Delta equals 4 corresponding to 2 curvatures. You've got 2 curvatures. So there are more renormalizations than you would have had in QED, but hey, it's okay. Right? It's stabilized. So it's a finite number of renormalizations. You have to do these renormalizations. It's not finite, but it becomes renormalizable. The detailed proof of this involves a whole bunch of technology. One typically says word identities. Andrei Slavnov's a friend of mine, and actually there's a nasty theorem in the history of science that things tend to get named after the second person who did it. Anyway, one should not forget this Slavnov-Taylor aspect of this. Ward, of course, was for pure electrodynamics. Slavnov and Taylor for Young-Mills, and it's really, I don't think there's a particular name for the general covariance version of this, but in any case, they're similar identities. Actually, I sort of wrote them in pieces, whatever it means. But we tend to call them word identities. And then you have to analyze, there's this feature of quantization in a covariant fashion, what Rice DeWitt and Feynman called ghost fields. There's a whole bunch of technology that one could go through, but I'm just going to mention it here. This part of the theory involves studying the word identities carefully and analyzing and seeing that, in fact, you only encounter infinities of the same structure as what you have already. Okay, that's the good news. The bad news is, having included this term, it contributes additional degrees of freedom that you're not familiar with to the gravitational theory. You have ordinary gravity interactions. All of general relativity, free field general relativity is still there. But being a higher derivative theory, because you have curvature squared terms, it's fourth order derivatives, you have additional degrees of freedom, which when you organize it this way, you can see it's nicely polarized so that this guy produces massive spin 2. The r squared, by the way, produces mass spin 0. Come back to that in a second. But the massive spin 2, as you can see from Memoirs of the Academy of St. Petersburg, 1854. Sorry, I forgot his name, but anyway, famous paper about higher derivative theories. There's an alternation of signs. So, Ostrogowski, 1854. I actually have a paper, because I gave a talk in Kazan, and give a talk in a place like Kazan, we can actually extract the paper from their library. And so now I have actual, nobody else has ever seen this paper. Even in Cambridge, they can't talk about it. I have it. Okay. But it's the wrong sign. The kinetic term has negative sign that corresponds to negative energy. Shows you what to do about it. Okay. So these are, the word ghost is applied to these as well as to the Feynman DeWitt ghosts, Feynman-Popoff ghosts. Feynman-Popoff, by the way, is a classic example of naming things after the second thing he did something. These are gauge artifacts, and they have to be treated by Warded entities. These are really serious. You decide whether you like the theory or not. Okay, so like I said, there's good news and bad news. There's also interesting news. The R-squared term, as I've said, contributes a massive scalar, happily of positive energy, so nothing bad about it. In fact, it's rather attractive. The R-squared term is the key to Alexei Starobinsky's model, well, his second formulation of his model of inflation, which happens to be the best current fit to CMB data for early universe fluctuations coming from the planet satellite. So this is really popular. This is, I mean, probably the closest approach to real physics in our thought. And it makes you wonder if that's really part of the gravitational action, its brother, we should figure out what to do about it. It can take, depending on whether you feed the Italian wine or Spanish wine, and wax one or the other, depending on the day. I've studied it, but I don't know what I entirely think about this whole subject. But indeed, R-squared inflation is the closest we come to really a contact between quantum gravity and cosmology. There's, okay, some maybe good news. We come back to the renormalizable theory with the alpha coefficient, which is the coefficient of Weyl squared. Okay? The one that's problematic, but which is key to making it renormalizable. Well, you can do the one-loop calculations. Fredkin and Seitlin, and then Avramidi and Barvinsky. There was an earlier paper by Bove and Antonin, but that paper was wrong. I didn't list it here, but first correct paper of Fredkin and Seitlin. And in particular, is emphasized by Avramidi and Barvinsky correctly, this point. If you write alpha as 1 over G2 squared, 2 for spin 2, massive. It's the way that one handles the Yang-Mills action in the strong interactions. And as in Yang-Mills, it's asymptotically free. G2 is asymptotically free, meaning that the limit is 0. Now G2 controls the coupling of these higher derivative interactions, and so maybe they're not so critical. Well, that was a point of view that gives rise to a certain hope that maybe you could just dodge the bullet. This would be a relation to asymptotic safety, where there are a lot of considerations that maybe in a gravity theory, you can go out of perturbation theory. What we have is not a Gaussian fixed point is one where all the coupling constants are 0. A non-Gaussian fixed point is one where they reach a non-zero value. So we have things that we're interested in and would like to keep, please. Newton's constant and the cosmological constant. So there could be a non-Gaussian fixed point for those, together with value 0 of this coupling G2 for the higher derivatives. And so you could hope that maybe there's some trajectories that never pass through the spin 2 ghost point. Okay, so this is a point of view that has been followed by Niedermeyer, it's actually Hermann Nicolai's first student, who suggested that what we call the Hessian matrix, the matrix of second derivatives as you go along the renormalization trajectory, could be free of negative eigenvalues for appropriate trajectories. So here are a whole bunch of trajectories ending on a fixed point for Newton's constant and the cosmological constant, but with G2 tending to 0. So does that mean you can really dodge it? Well, he said depending on the trajectory, maybe it's one of these blue ones, there can be some trajectories we don't run into that hole. And there's kind of a virtual presence of these interactions which you never actually hit. Kind of like they're unstable. It's okay. That's another whole seminar to go into that. I just mentioned this as an attitude that one can take, and there are lots of discussions about this. But I mentioned this as it's maybe a desperate attitude towards the problem of the ghost. Let's see. There's some other news, however, that's interesting, which is that if you take these curvature terms, quadratic curvature terms, seriously, they give rise to an enlarged set of static classical solutions. I was just talking about the dynamical ones where we have these propagating masses in two fields, unfortunately with the wrong sign. But it also changes the static solutions, and they're interesting. There's wormholes that can go from one universe to another through a finite cycle. This is great for Hollywood. Okay. There are solutions that approximate the Schwarzschild solution, the black hole's solution at large distances, but become, they don't have a horizon. And there are solutions that do have a horizon, but are not of Schwarzschild type, but which have a kind of a trading of the baton in the relay race. The Schwarzschild solution at small sizes in this theory becomes, the Schwarzschild solution is also a solution in the size of the theory, but at small masses it becomes unstable. Down at the regime perhaps where Hawking is talking about radiation of black holes. But the non-Schwarzschild solution, which crosses the Schwarzschild family at a certain point, called the Rsquared point, it seems that the non-Schwarzschild black hole solutions become stable. So there are all sorts of interesting aspects of the consequences of having a curvature square term. And so that's worth studying. However, I'm going to jump now to the other track, sort of the Dirac track, which is trying to find a theory with magical cancellations between the various infinities. So I'm going to start this discussion in 1976 with the discovery of supergravity, Riemann, van Nieuwenhuizen and Ferrara, and Desser and Zumino. And there are important cancellations in supersymmetric theories. Supersymmetric theories involve symmetry between fermions and bosons. We have two broad families of particles in physics. Bosons with integral spin in terms of Planck's constant. Fermions integral plus 1/2. And they behave in the aggregate very differently. Bose-Einstein statistics for bosons, they're happy all to be a great big family at the same quantum state. They don't mind it at all. There are certain statistics for that. Bose-Einstein statistics for fermions, because of the Pauli exclusion principle, you cannot have two fermionic state particles in the same state. So they resist one another, and as a result, you get solid matter. You remain largely like fermions. Forces, light, gravity, and so forth, are bosons, and Higgs particles. Okay, so but in supersymmetric theories, you have symmetry between the fermionic and bosonic particles, called supersymmetry. And there was a hope that local supersymmetry, generalizing the local general covariance of Einstein's theory, could give rise to a cancellation of the ultraviolet infinities. And indeed, there are non-renormalization theorems in rigid supersymmetry which give rise exactly to this. In the potential, the masses and the potentials of non-gravitational supersymmetric theories, you can see they are not renormalized. And this is exactly one of the reasons why they built such an expensive machine in Geneva. These non-renormalization theorems are giving rise to a degree of control over supersymmetric theories that is related to the possibilities of unification of forces, and that's one of the key aims of the Large Hadron Collider. We'll go also into a seminar about the supersymmetric aspects of hopes for unification at the LHC. So, a way of understanding the supersymmetric, I could give another little Blackboard discussion, but maybe I'll do that later on if you want. They're most easily understood from a formulation of supersymmetric theory in what we call superspace that includes coordinates, ordinary bosonic commuting coordinates, x mu, space-time, and anti-commuting spinorial coordinates called theta alpha. So these are funny numbers. If you multiply them together one order, the other order costs you a minus sign. And if you have psychological problems about that, I can give you a little discussion involving Valuya, which will make you feel better. But it involves gamma receipts. Okay. But anyway, this is a formulation where the divergent cancellations become particularly clear. So there was hope that maybe supersymmetry does the job. So you have to go back and study the counter terms, okay? This is similar to the non-abelian gauge symmetries in Mills theory and general covariance. So as we've seen, you have to use the Ward identities, Ward-Slavov-Taylor identities, whose solution set determines the eligible counter terms. Once you find eligible counter terms, then, well, until you've done the calculation, you don't know anything, strictly speaking, other than the fact that there could be such an infinity. But Murray-Gell-Mann announced his totalitarian principle. Everything not forbidden is compulsory. So if there's a possibility of something bad happening, you can be sure it's going to happen. I just lost my suitcase to the British Airways yesterday. I knew at the airport was going to happen. It's a clear example of the totalitarianism. Once the baggage delivery belts at Heathrow Airport were not working, I knew this has happened to me before. Okay, so everything not forbidden is compulsory, and don't believe what the airline people tell you. So, indeed, at two loops, the curvature cubed counter term that's allowed by the Ward identities, we call them Ward identities for short. Reminded people of Slavov and Taylor. Indeed, was found by Grof and Zaniotti with this curious coefficient, 1 over epsilon dimensional regularization. Now, in supergravity, you have to do the same thing, but taking into account supersymmetry. And the algebra, now you run into a special property of supersymmetry. The algebra of local supersymmetry transformations, in many, but not all, representations that you need to write the theory in terms of actions, only closes on a finite set of transformations when the fields are subjected to the classical field equations. What does that mean? These are called on-shell algebras. If you don't want to do that, you're free to consider the algebra of the transformations which the action is in fact invariant under, and you calculate the algebra. The problem is the algebra sort of erupts into an infinite series of transformations that don't do very much. They transform one field by the field equation of another field, the other field by the field equation of the first field, and there's a whole bunch of transformations that end up doing nothing on the mass shell, but they complicate their life. So it's what we call on-shell representations when you have this problem. One of the tasks was to look for off-shell representations where you really have a clear finite component representation of the algebra, and that has bearing on the infinities problem too. Now you can handle the such representations by Ward identity analysis, but laziness comes in, and basically people say, ugh, and get disgusted and don't look at it. Right? However, if your aim is limited, first of all, let's impose the classical field equations. Secondly, let's look for the very first infinity. Okay? So, subject to the classical field equations in pure relativity, you'd be looking at the two-loop infinities. The first one is really dangerous to you. Yeah, Gell-Mann warns you, and it happens. So if you take that attitude, the analysis becomes more feasible. And when you do it, taking into account supergravity's supersymmetry, the first possible candidate doesn't happen at two loops, but it happens at three, where delta equals 2 times 3 plus 2, which is 8. 8 derivatives. You have to watch out that the things don't vanish subject to the classical field equations. You have all these cancellations that happen in one loop. It eliminates a whole bunch of things. There is one term ordic in curvatures. 2, 2, 2, 2, that's 8, okay, which you have to worry about. It's a Riemann to the fourth structure, plus, of course, the fermionic gravitino completions. And this is what we found with Stanley Deser and John Kay. It's the square. Now, here we come into Spanish physics. Well, I just confirmed it earlier. It is, in fact, it's related to Barcelona, I believe. And you have to, it's Luis with 2 L's, which warned me that actually we did want to come on here. And I found this paper just this morning. So, Bell-Robinson squared, in fact, is the purely gravitational part of the candidate at 3 loops for the first serious supergravity infinity. The Bell-Robinson tensor has a property that it's like a stress tensor for gravity. And it is used in gravitational discussions to gravity waves. If you want to show the energy content of a gravity wave, you can't talk about an ordinary stress tensor, because there's no good covariant, generally covariant ordinary stress tensor, but there is the Bell-Robinson tensor. It's purely symmetric in the 4 indices. It's purely traceless on any pair of indices. And it acts like a stress tensor, and indeed, that's what's coming up. It's also sort of the grandfather of all important quantum corrections in supergravity and string theory. There's a little historical anecdote of how we came up to this, because we almost wrote a paper saying there were no infinities in supergravity, and I was particularly glad that we didn't mail it, because John Kay and I were this is for just chewing the fat and say bullshitting one afternoon. And we said, it's clear that no such tensor can exist, because the tensor would have a list of specific properties, including the ones I just mentioned, would have a name. So we said, what are the tensors with names? Levi-Civita tensor, well, it's clearly not that. Riemann tensor, it's not that. And then I remember John or I said, and the Bell-Robinson tensor is clearly not that. And then, well, what is the Bell-Robinson tensor here? So we wrote a telephone book in Wiesner, and Wheeler, page 846 or something like that. Bell-Robinson, totally symmetric, conserved on any index, totally traceless. Oops. So that was in fact how we came to realize the structure that you had to have for the first dangerous counterterm in supergravity. Now, to this day, it's a 3-loop calculation. We don't know the answer. What the coefficient of that is in pure supergravity, pure n equals 1 supergravity with 1 gravitino field. Now, strangely, rather a lot is now known about such counterterms in extended supergravities. You can have more gravitini, and you can go up to 8. It's the largest supergravity theory in 4 dimensions. It's a glorious theory. 1 spin 2, 8 spin 3 halves, 28 spin 1, 56 spin 1 half, and 70 scalars. It is very nonlinear. Not only the gravitational nonlinearity, but the scalars. In fact, their target space, the space they value, their nonlinearity is described by their taking the values in the coset space of E7, the group over SU8. It's another whole seminar on how that happened. It's called a duality symmetry. It's a wonderful theory. Whether it's directly related to reality or not, we don't know. Herman Nicolai loves this theory. He has other uses for it. But we can talk about the infinities. Now, this becomes a story of why models are best. It's over more than a decade, almost getting a decade and a half now, I've been having an ongoing discussion with Bern about these kinds of issues. Now, there's a particular approach to calculating diagrams. Bern, Carrasco, Dixon, Johansson, Kossor, Roybal, and mixtures of others as you go over probably 20, 30 papers. Another approach to calculating amplitudes, which is not just Feynman's approach. It employs crucially the property of unitarity of amplitudes, together with dimensional regularization, what's called the optical theorem in ordinary quantum mechanics, but now employed with properties of dimensional regularization, and keep all the terms as you go away from 4 dimensions and use them in clever ways. This allows calculations to be done with other techniques as well. Bern, Carrasco, Johansson, BCJ techniques, and so forth. It allowed them to get to the 3-loop level. Here are the diagrams. If you do this in ordinary Feynman diagram fashion, it would involve about 10 to the 20th terms. You can see that no graduate student's going to do it that way. And in fact, at 3 loops, they vanish. Coefficient is 0. So is this just a miracle, or can we back up and understand it? So we had a look at that with Guillaume Bossard and Paul Howe, and what we call a counterterm counterattack. And in fact, there are indications that there's a non-Lorentz covariant formulation. If you give up manifest Lorentz invariance, you can see a little bit more. There could be a formulation in which, I mentioned on-shell and off-shell before. If you have an off-shell formulation that you don't have to impose the classical field equations, you really have a finite component formulation, you get stronger non-renormalization theorems. The naive non-renormalization theorem for maximal supergravity, which has 32 supersymmetries, if you look at what seems to be the maximal possible off-shell formulation, is what we call half supersymmetric. That's 16 supersymmetries. Every theta integration corresponds to 1/2 dimension in power counting. We're down to 8. After 16 is 8. That's hard in the fourth. You're looking again at this kind of a counterterm. But you can see from a two-dimensional analysis that maybe you can get one more in the non-Lorentz covariant formulation. 17 would do it. All you need is just a little smidgen extra. And that could rule out the 3-loop counterterm. Okay? So that would push the boundary to 4 loops. This made me brave enough to get involved in a bet with Heisenberg that there would be divergences at the 4-loop level. So I'm not going to write all the diagrams now that there are 50 total topologies. And I bet a rather good bottle of wine, a good Barolo, and I lost it. I lost it at 4 loops too. And to pay a fine bottle of Barolo, bought from a Rome wine cellar, recommended by Elias Geritzis. Anyway, so Zvi drank that bottle together with his wife at their wedding anniversary, and then finally, because it's getting harder and harder, even for these unitarity guys. Now, as I tell you, that laziness played a role in this story. There are these highly nonlinear word identities for things that you really don't want to look at, but actually, the nonlinear E7 symmetry can be handled when we have to develop a range of techniques for dealing with this cohomological renormalization and so forth. Again, seminars we could give about that. And we came to understand that this E7 symmetry plays an important role in governing the infinities as well as supersymmetry. And this, in fact, interdicts the counterterms in 4-dimensional space-time through the 6-loop order. And so actually, we go well beyond 4, 5, and 6. We're telling the and company, yeah, it's going to be finite all the way. Don't surprise us there. We'd be very interested in the calculations, but we think 0. 7 loops now becomes the boundary. Now that's rather high even for these unitary guys. And the payoff of the next bet was reduced in amplitude to an English line versus a good California line. Kids Cody Bacchus, I'll tell you about the ball. Ball has smuggled it through US customs. And it was tangentially settled, let's say that, at 5 loops in 2018. This 7-loop counterterm corresponds to delta equals 16 in power counting. Generically, d to the 8 r to the 4th. You can see 8 plus 8, plus the supergravity completions. Now, they didn't do the 7-loop calculation, but they did do a 5-loop calculation in general dimensions. The same, remember the d-2 factor here. If you go to higher dimensions, things happen earlier, and they can look at things in fractional dimensions as well. And you can see that dimension 16 corresponds to 24 over 5 dimensions at the 5-loop level. If it didn't happen then, there would be a delta equals 18 counterterm, generically d to the 10th r to the 4th, the next thing to worry about, which people have very few doubts whether it's going to occur, but that would occur at 26 over 5 dimensions. And sadly, actually, I was kind of looking forward to losing this one. I thought it would be exciting, maybe really the beginning of something, but actually we won. Paul and I won. They do occur at 24 over 5 space-time dimensions, corresponding to the anticipated d to the 8th r to the 4th counterterm. The detailed structure, again, is interesting, involving the way the E7 invariance is realized, but we've won 2 bottles of a very good California wine. Nice living here. Okay, so where do things stand? That calculation is marvelous. I mean, in fact, there are techniques which now involve unitarity, relation with Yang-Mills and development of machine computation, because the number of their diagrams is getting out of control. They think maybe they can go on to higher orders, but in any case, their techniques are also useful for the LHC and in other contexts. For gravity itself, it seems that this result is likely the end of the hope for miraculous ultraviolet cancellations. It takes an awful long time before it starts behaving like Heisenberg predicted in maximal supergravity. Now, of course, I've been talking about field theory throughout this whole talk. There's another theory that we have that's perfectly ultraviolet fine, and it's called superstring theory, where the infinity in the art of the fourth counter term becomes replaced by a finite number, which involves zeta of 3. And so, these terms are present in the expansion of superstring theory with known coefficients, finite coefficients. You can also use superstring theory as a rather expensive regularization of field theory, and see what happens as you try to take the field theory limit of string theory. You see the infinities come back, and indeed, that analysis is Caroline Hope and Michael Green, it agrees with the Stelle prediction. So what we're seeing is something about the relations between string theory and their field theory limits. We've learned that field theory, it looks like it's ultimately capitulating to Heisenberg's warning about ordinary field theories of gravity. But there's this enormous long pause that has something to say about the physical aspects of string theory. And I don't really know what to say about that, but I think the language good anyway. So, thanks for your attention.